This is a great question. Certainly going to set you up for the FRQs from this chapter, where we have I already drew the slope field, obviously. I didn't want to walk you through that again. You can see some of my key points over here, key coordinates, and then key y primes. And then it says for part B, let f be the function that satisfies the given differential equation. Again, the given differential equation is right up here. And again, we're going to let f be that function that satisfies that one. Write an equation for the tangent line to the curve through the point 1, 1. Okay, so we know that we need a point and we need a slope to come up with the equation of a line. Okay, and that happens to be the tangent line to the curve right there. And we know that at the point 1, 1, which you can kind of see there that I drew, that the slope is 1/2. So we can easily come up with the equation of the tangent line. Y minus 1 is equal to 1/2, which is the slope. Multiply that by x minus 1. And if we let f be the function, let's do this. Let's let it be f of x, equaling 1/2 x, and that's minus 1/2 plus 1. So if we're going to add 1 to both sides, we have minus 1/2 plus 1, which gives us plus 1/2. Okay, so we have a slope of 1/2, and we have a y-intercept of 1/2. So we just go ahead and draw that tangent line right there at the point 1, 1. Okay, and again, that's the equation of the tangent line. F of x equals 1/2 x plus 1/2. And what else do we need to do? Use your tangent line equation to estimate the value of f of 1/2. And so, did I say 1/2? F of 1.2. So 1.2 is, here's 1, and 1.2 would be right next to it there. And so somewhere over here we can see that the estimate of 1.2 is going to be lower. And I think that they're going to ask that down there somewhere probably. But for right now, we want to estimate f of 1.2. We don't know what f of 1.2 is because we don't know what the y is equal to yet. We don't know the actual solution to the differential equation. So again, this f of x here is not the antiderivative of this differential equation, of this, it's not the antiderivative, it's not a general solution, it's the equation of the tangent line. So if we want to estimate what f of 1.2 is, we would replace x with 1.2. So we have half of 1.2 and then plus 1/2. Okay, so instead of just trying to kind of do that in my head, we'll just do 0.5 times 1.2, and we add to that 0.5, and we get 1.1. Okay, amazing when you make videos, you don't try to do things in your head too much. So 1.1 is my estimate for the value of f of 1.2. Okay, so that's what we just did there. That's our tangent line approximation. It's a linear approximation, so that gives us some more practice with that. And then find the particular solution. Okay, so we want the particular solution to this differential equation, and that's kind of a neat thing because you haven't seen that yet. Okay, and we're going to actually use our solution to find f of 1.2 so we can compare it to what we had here. And the initial condition, f of 1 equals 1. Well, let's do that in the little workspace right up here, where if we take this equation here, and this is a brand new thing, but it's super important. This is what we call a separable differential equation. And do we really want to do that? Particular solution. Wow, I'm not sure that we know how to do this yet, but let me just walk you through it anyway. We have our dy dx. And so what we're going to do is notice that we have a y over here and a y over there. Well, if we divide both sides by y and multiply both sides by dx, okay, then we're going to get dy over y is equal to x over 2 times dx. Okay, that's what we just did. We separated the variables. And so the y goes with the dy, the x goes on the same side as the dx. I should point out that not all differential equations are separable differential equations. In other words, you can't separate the x and the y from one another and get them attached to or somewhere close to their dy counterparts. And so let's rewrite this left side as 1 over y dy equaling x over 2 dx. Now here's the cool thing, you can actually integrate both sides. Okay, if you integrate both sides, then, well, you have to find an antiderivative of 1 over y dy. Well, what's the antiderivative? Well, yeah, we haven't talked about this one yet, but so I'm just going to tell you. The antiderivative of 1 over y would be the function whose derivative is 1 over y. Okay, so maybe that gives you a little clue, and maybe some of you got it already. But the function whose derivative is 1 over y is ln of y. Okay, so we have ln of y is the antiderivative of 1 over y, okay, or an antiderivative, and equals what's the antiderivative of x over 2? Well, the antiderivative of x over 2 is x squared over 2 over 2, so that's x squared over 4. Okay, and then we have a plus c. Now, we haven't really talked about that, so I'll bring that up now. You could put a plus c on the left and a plus c on the right, but now that you're in calculus, you get to actually have a little freedom with the plus c's. If you have a plus c on the left and a plus c on the right and you subtract them, they don't just cancel out, okay, because one could have a different c than another. So you'd actually do a plus c1, let's do that, plus c1 and a plus c2. So these could be different constants. If they're the same, you'd cancel them out. But then if you subtract c1 from both sides, then you'd get ln of y equals x squared over 4 plus, now you have some constant minus another constant. Well, guys, that's just a constant, okay? So that's why we would write it as just x squared over 4 plus c. As long as you put a constant in there, it's just a constant. All right. So that being said, let's figure out what this constant's value is. And to do that, we can use this equation here because we know that the initial condition is f of 1 is equal to 1. So that's way over here. Remember, f of 1 equals 1. This graph of the particular solution went through the point 1, 1. So that means when x is 1, y is 1. So we're just going to put a 1 in for y and a 1 in for x. And we're going to solve for c. So we've done this already. Okay, doing the solving the initial value problems. And you should recognize quickly that the ln of 1 is 0. And 0 is equal to 1/4 plus c. So therefore, c is equal to negative 1 over 4. Alright, so that's great. So therefore, our equation would be ln of y. Yeah, that's not going to be great, but it is our equation. ln of y equals x squared over 4 minus 1 over 4. But we don't really want ln of y, we want y, right? So we know from our vast knowledge of pre-calc honors that if we take this equation and we convert it to exponential form, we have e to the right side is equal to y. And so we have y equals e to the x squared over 4 minus 1 over 4. Kind of opened up the big can of worms here with this part C. So anyway, we're going to go ahead and plug this into our calculators anyway. This is our actual particular solution to the differential equation, and we're going to use it to find the actual value of f of 1.2. And my calculator is going to get that out, and let's see if I can show the equation on the right. And then what we're going to do is a little technique that I like to use, and so I'm going to use it now. Let me clear out my functions. So we're just going to type in our y1 to be e to the, what is that, x squared over 4. So I'm going to put it in parentheses, x squared divided by 4. Okay, and I'm going to close the parentheses there. And then that guy right there is minus 1 over 4. So I could do 1 divided by 4. I could have done 0.25. And I'm going to quit that screen. Okay? And when I quit that screen, I can easily recall that y1, and I can input my 1.2. And remember what we said, that the f of 1.2 estimate that we used the tangent line for, we got 1.1. Now clearly you can see that due to the slope field, you can see that it's concave up. The slope field shows that the particular solution is concave up right there through this point, and therefore our tangent line approximation of 1.1 would be too low because of that graph of the function being concave up. Okay, so let's just confirm the fact that hopefully after saying all that, our approximation will be lower than what we actually get. And we do actually get a value that's a little bit higher than the 1.1. Nevertheless, it is higher in 1.183. Okay, so we have is approximately equal, oops, that's not what we want. We want y at 1.2 is approximately equal to 1.183, and so there's our actual value at 1.2, and we compared our estimate found in part B to the actual value. We saw that it's higher. Was your estimate for part B an underestimate or overestimate? We already talked about that. Use your slope field to explain why, and that was again because f is concave up, and it's an underestimate, concave up over the interval right around there. And so we can see on the interval from 1 to 1.2. So really we just need to make sure that our function is concave up over the entire interval, and that way we can determine that our linear approximation is in fact too low. Okay, so this is something we're going to spend a ton of time on. That was maybe a little bit overwhelming for one video because I introduced a lot of new stuff there, but nevertheless that is a very important problem, okay, which we again will